Okay, so in the last hour, I introduced the vector iteration method, or sometimes it is called the power method. And the reason why we call it the power method, since in each iteration we are increasing the power of the vectors. Okay. In each iterations, sometimes we are not only calculate the newly obtained vectors from the A inverse B times the previous vector, U vector, and also I say that sometimes we will do the normalization to get to normalize the obtained vector. And also sometimes we will calculate the Rayleigh quotient. What is the Rayleigh quotient? If we got the UI That's the definition for the Rayleigh quotient, and the UI vector means in each iterations the newly calculated the U vector. So the UI is obtained from the UI minus one, and the UI minus one is the vector in the previous iterations, and for this, if we calculate this one, this actually it is a scalar, and for this scalar there is a name, we called it the Rayleigh quotient, and after many iterations, the UM will approach to the X, the eigenvector, and the Rayleigh quotient will approach to the eigenvalue. Okay, so after several iterations, the iterated vector will approach to one of the eigenvector, and the Rayleigh quotient will approach to the eigenvalue. Okay, so then I will prove why the inverse iteration method will approach to will help us to get the approximate eigenvector and the approximate eigenvalue. And let's say the lambda 1 Okay, so right now I will give the definition of the subscript. The subscript of the lambda 1 will be the eigenvalue with the minimum absolute, and the lambda 2 is the next small eigenvalue. So the absolute value of the lambda 1 will be the smallest in all the eigenvalues. The lambda 2 is greater than lambda 1 but less than lambda 3 until the lambda n. So it is different from the Jacobi's method. For the Jacobi's method, we don't need to care about the definition of the lambda 1, the lambda 2, since if we use the Jacobi's method or the generalized Jacobi's method, we can get all the eigenvalues and all the eigenvectors after we solve the problems. And the sequence of the eigenvalue is not so important. You will not, for example, the first columns of the eigenvalue of the eigenvector or the first eigenvalue obtained from the A11 divided by the B11 is not always the smallest eigenvalue. Okay, it is just one of the eigenvalue. Okay, but for the power method or the vector iterations method, the sequence we need to define clearly. The lambda 1 is the smallest one. Okay, so then in the solution procedure, we will assume an arbitrary initial vector, and the arbitrarily assumed vector can be any vector. Okay, it doesn't matter how do you assume the vector. It can be any one. And remember, the eigenvectors can always form a set of the basis vector for the n dimensions vectors for the considered problems. Okay, so that's the assumed vector. The assumed vector, there's n by 1. And we know it must, since the eigenvectors, they are normalized to, they are normal to each other, and all the eigenvectors, they must be independent vectors. However, sometimes we could have one eigenvalue, but there are two corresponding eigenvectors. If the eigenvalue is a double root solution for the characteristic equation, then we can get two independent eigenvectors for the same eigenvalue. Okay. However, if the matrix A and the matrix B, they are the n by n matrix, so we can always find n independent eigenvectors, and the eigenvectors can form for any U0 vector, we can always express the U0 vector as a linear combinations of all the eigenvectors. And the alpha 1, alpha 2 until the alpha n, they are the real numbers. They are the real numbers. We can always find these expressions for any assumed initial vector U0. Okay, then remember the AX1 is equal to lambda 1 B x1, and the AX2 is equal to lambda 2 bx2. Okay. Also, the okay. From these equations, we can multiply the A inverse to both sides, and also we can divide lambda 1 to both sides. So we can get A inverse B times x1 will be equal to x1 divided by lambda 1. And the same equations can be applied to all. So the A inverse B x1 will be equal to 1 divided by lambda 1 x1. A inverse B x2 will be equal to 1 divided by lambda 2 times x2. Okay. So if the u0 can always be expressed like this one, then what is the u1? Okay, we know the u1 is obtained from the, we need to multiply the A inverse B to the u0. We need to multiply the A inverse B to the u0 to get the the u1. And if we change the expressions for the u0 from the previous equations, then it will be the alpha 1. Okay, so it will be the u1 will be equal to this formula. If we replace the u0 by the right hand side of these equations, then we can get this one. And from the previous derivations for these equations will be equal to 1 divided by lambda 1 x1. This one lambda 2 x2. Okay, so so this one will be equal to this one, and then we can take out the lambda 1. Okay, then we can take out okay. So that's the u1 vector. That's the u1 vector. And after we got the u1 vector, we will keep on the iterations, and we can use the obtained u1 to calculate the u2 vector. Okay, so that's the u1 vector. And what will be the u2 vector? The u2 vector is equal to the A inverse B times u1. The u2 is equal to the A inverse B times u1. And then we can replace this formula into these equations. So it will be the I forgot the alpha 2 and alpha n here. Remember, we still have the alpha 2 and alpha n. Alpha 2 times So after we replace these equations into the first equations, then we can get the formula like this one. We can get the formula like this one. And again, we can do some, we can change some of the expressions. Okay, so let's change it all the expressions. So this one will be equal to, and this one. Okay, so as long as we multiply the A inverse B to any eigenvector, then it is equal to this one. So we can change these expressions again. So it will be we can take out the lambda 1 squared. Okay, so the U2 will be equal to this one. So we can keep on the solution procedures, and after we got the U2, we can calculate the U3. After we got the U3, we can calculate the U4. So we can keep on these iterations. So after n iterations, what will be the UN? Okay, and also by the definition, the lambda 1 is always the eigenvalue with the minimum absolute, and the lambda 2 is greater. The absolute values of the lambda 2 will be greater than the lambda 1, and the lambda 3 is greater than the lambda 2. So we know all these, they are less than 1. And we know the lambda 1 divided by lambda n will be the smallest. If we calculate the absolute, this one will be the smallest. This one is greater than the lambda 1 divided by lambda 3. But it is still a number less than 1. Okay, if the lambda 1 divided by lambda 2 or lambda 1 divided by lambda 3 until the last one, the lambda 1 divided by the lambda n, they are all less than 1. They are all less than 1. So after many iterations, we can increase the power of this ratio. And if the lambda 1 divided by lambda 2 is always less than 1. So after we increase the power, we can say this number approaches to 0. They are always approach to 0, especially compared to the first term. Compared to the first term, the second term, the third term, until the last one, the nth term, they will become smaller. Compared to the first term, they will be smaller and smaller. So if the second term approach to 0, the third term approach to 0, then the vector will approach to x1. Okay, so if we keep on the iterations, the will always approach to the x1, and the so that's the proof why if we use the inverse iteration method, the first approximate vector for the eigenvector will be always the vector corresponding to the minimum absolute lambda 1. Okay, so the first converged vector will approach to x1. Times constant. Okay, so the will approach to the x1, and also the Rayleigh quotient will approach to lambda 1. Okay, also we can prove the approaches to x1. The Rayleigh quotient will approach to lambda 1. Also, you will find the convergence of the Rayleigh quotient to the lambda 1 will be faster than the approach to x1. Okay, since when we calculate the Rayleigh quotient, the ui transpose A ui divided by ui transpose B ui, and the Rayleigh quotient will approach to the smallest eigenvalue lambda 1, and the rate of convergence is even faster than the convergence of the eigenvector. Okay, so that's the inverse iteration method. Also, there is another iteration. There is another iteration solution procedure, which is called the direct iteration method. If we use the direct iteration method, so it means the U1 is calculated by the B inverse A U0, and the U2 is obtained by the B inverse A U1. So we will use the B inverse A times the initially assume the U0 vector. Then we can get the U1. After we got the U1, we will multiply the B inverse A to the U1 to get the U2. Okay, so in this solution procedure, it is called the direct iteration method. You must notice the difference between the inverse iteration and the direct iteration. If we use the direct, for the inverse iterations, we use the A inverse B 2 times U0. But for the direct iteration method, we use the B inverse A times U0. Okay. That's the direct iteration method. Again, the lambda 1, that's this. Again, remember the subscript also represents the absolute value. Also the lambda 1 is always as that. And also remember the ax1 is equal to lambda 1 bx1. Okay, so it means the lambda 1 and the x1 they form a set of the eigenpair, and the eigenpair include the eigenvalue and the corresponding eigenvector. So the lambda 1 and the x1, they are the first eigenpair. If the lambda 1 is corresponding to the x1, then this equation is the valid equations. So that's why we say the lambda 1 is the eigenvalue, the x1 is the eigenvector, since they can fulfill these equations. And then what will be the B inverse A? The B inverse A x1. So if we calculate the B inverse A x1, it will give you the lambda 1 x1. And also the B inverse A x2 will be equal to the lambda 2 x2 will be equal to the lambda 2 x2. Okay, so that's the we can just calculate. Okay, so the direct iteration method. Okay, so also remember for any vector u0, we can always express it as the linear combination of the eigenvector. Okay, no matter what is the u0 vector, we know they can be always expressed as the we can express the u0 as the combinations of this vector. Okay, then what will be the u1? The u1 will be equal to the B inverse A times u0, B inverse A times u0, then we can get the u1. Then we can replace these expressions into this formula. So it will be the alpha 1 B inverse A x1 plus alpha 2 B inverse A x2 plus alpha n B inverse A x. Okay, so we can get the formula for the u1. Then we can get the formula for the u1. And from the formula in the previous page, we know in these expressions, this one can be replaced by the lambda 1 x1, and these expressions can be replaced by the lambda 2 x2, and also these expressions is the lambda n xn. Okay, so This time we will take out the lambda n. Okay, if we take out the lambda n, then the semi-equations should be something like this one. Should be something like this one. Okay, so this one is the u1. And how can we get the u2? The u2 is obtained from the B inverse A times the u1. Okay, so we can multiply the B inverse A to these expressions again. Then we know what will be the u2 vector. What will be the u2 vector? The u2 vector should be equal to the lambda n squared times alpha 1, lambda 1 divided by lambda n squared times x1 plus alpha 2, lambda 1 divided by lambda n squared x2 plus alpha n xn. Okay, so that's the expressions for the u2. And after several iterations, un Okay, so as long as the number of the iterations increase, also the power of the ratios will also increase. So the un will be equal to this one. And since the absolute value of the lambda n is the largest one in all the eigenvalues, so we know the ratio alpha 1 divided by lambda n is less than 1. Also the lambda 2, the lambda 2 divided by lambda n is also less than 1. So after we increase the number of iterations, those coefficients the coefficients of the x1 and the x2, they will relatively smaller than the last term. The values of this one will go to 0. If we compare the ratios raised to n, the second ratio raised to n, compare to the coefficient of the last vector, which is always equal to the alpha n. So after the increase, we increase the number of the iterations. The first n-1 terms will approach to zeros. So for the direct iteration method, the un will approach to xn. Okay. If we use the direct iteration method, in each iterations we can increase the power for the ratios. So the ratios will compared to the last term is they will be close to zeros. So the vector, the largest, if we use the m increase, the vector will approach to the xn. The xn is and the Rayleigh quotient the Rayleigh quotient will approach to the lambda n. Also remember if we compare the convergence rate, the Rayleigh quotient approach to the lambda n will be faster than the approach to the xn. Okay, so we can use either method. We can use the inverse iteration method. Also, we can use the direct iteration method. It depends on which eigenvector we like to get in the first state. And if we use the inverse iteration method, we will get the lambda 1 and the corresponding x1. But if we use the direct iteration method, we will get the lambda n and the corresponding xn. So it depends on the problems we need to solve. And so the eigenvector with the minimum eigenvalue, or the eigenvector with the maximum eigenvalue, which one we like to get first. And for the structural dynamics problems, okay, so that's the equations for the structural dynamics problems. If we use the mathematical problems, we can say it is eigenvalue problems, and that's the. But for the structural analysis, for the structural dynamics problems, we know the K matrix is the stiffness matrix. The M matrix is the mass matrix, and the U vector. Sometimes we call them, they are the mode shapes of the structure. And the omega square, the omega is the natural frequency of the structures. Okay, so if the dimension of the stiffness matrix K and the dimension for the mass matrix, if the dimension is the n by n matrix, then we must have n eigenpairs. So we can solve n eigenvalues. Also, we can solve n eigenvectors. And we can solve all these n eigenvalues. Although so far the power method or the inverse, either the inverse iteration and the direct iteration method, we can get only one set of the eigenvalue and the eigenpair. Okay, I think I will stop today's course, and I will continue it tomorrow. So very fast you will get the next videos.